You might know APRS location trackers on 144 MHz. And you might have heard of LoRa, a relatively new modulation standard capable of bridging unexpected long distances at low power. Combined with cheap hardware and an innovative Austrian project, gets us an exciting mix: LoRa APRS trackers. Hello wireless enthusiasts! Here is the channel with a strange Swiss distortion in the signal, with a new episode around wireless and other exciting stuff. Make sure you subscribe if you do not want to miss the following emissions. In this video we will cover the basics of APRS as well as LoRa, build a LoRa APRS tracker, build a LoRa APRS iGate, which also can be configured as a Digipeater. See how we can display positions of trackers. The Automatic Packet Reporting System, short APRS, was invented in the 1980s by Bob Bruninga and is also used today to transmit position reports via ham bands. In Europe, we use 144.8 MHz. And in the US, they use 144.39. I do not know where standard APRS networks on 70 centimeters are operational. The APRS system consists of the following parts: trackers, Digipeaters, iGates, the APRS network, and sites that store and display the positions. The origin of a message is the tracker. It transmits its message via air to either an iGate or a Digipeater. The Digipeater retransmits messages till it hopefully reaches an iGate or its destination. The iGates transfer the message via the internet into the APRS network, and finally it arrives at places like aprs.fi, where it is stored and displayed. Only one frequency is used for all messages. That is why Digipeaters should not retransmit messages endlessly. As we will later see, the path determines how often a message will be retransmitted. Modern VHF handhelds like the Anytone 878 have a GPS built in and automatically transmit your position if you want. You also get special tracker hardware for the purpose, but unfortunately it is not cheap. These trackers have at least 1 watt output and consume quite some power. Trackers are also used for balloon tracking, by the way. A few years ago, Semtech invented and patented a new transmission protocol for low-power IoT devices. They called it LoRa, long range and low power. To reach this goal, they reduced the transmission speed. Why were they able to patent it? Low-speed frequency shift keying systems are known forever, because it is pretty different from FSK modulation. Its bandwidth is 125 kHz and not only 10 kHz of regular FSK APRS. Usually we reduce the bandwidth to get better sensitivity. Not here. They can get much more sensitivity, particularly with low data rates with this big bandwidth. Keep in mind, 10 dB more sensitivity at least doubles the range. Instead of 2 constant frequencies, they use a chirp signal, which changes its frequency for each bit and makes it less prone to frequency inaccuracies. This is an advantage because you can work with cheaper quartz crystals, and for satellites it can handle the Doppler effect quite well. This is why many newer CubeSats use this protocol instead of FSK. LoRa uses the concept of spreading factors. SF7 is fast and therefore has less range. SF12 is the slowest mode with the best range. Spreading means that the information is spread throughout the transmission to get redundancy. A short disturbance cannot harm the signal. LoRa APRS uses SF12, which has the disadvantage that one message is long and blocks the frequency for some time. But its range is excellent. Do you want proofs for this enormous range? A few years ago, I was able to bridge 203 kilometers with a 7 centimeter long antenna and a few milliwatts, and I regularly get signals from LoRa satellites over 2,000 kilometers. You find the world record video on my primary channel and a video on how to build such a satellite ground station on this channel. For the satellite ground station, I use a DIY ground plane and the same cheap receiver board we will use for our iGate. Fortunately, 433 MHz is also an ISM band, and therefore we get LoRa modules for these frequencies. And because this technology is made for cheap IoT devices, we get complete boards with an MPU, a display, a GPS, a battery holder, Wi-Fi, Bluetooth and LoRa for $35 delivered at our doorstep. The board is called T-Beam. In addition, we can print a cute case, and ready is our tracker hardware. Now we just need the software. Fortunately, Peter, OE5 BPA, took over an idea from some fellow hams in Vienna and developed an open source project. For somebody experienced with Arduino microcontrollers and Platform I/O, it should be possible to customize and install it in a few minutes. You find a quick start guide on the project page, and therefore I will not show how this is done. Currently, the guide is only made for an iGate. However, this is not a problem. Just download the files from the tracker repository if you want to program your T-Beam. The rest stays the same. However, I want to cover the configuration found in data/tracker.json. You have to add your call sign with an additional number like HB9BLA-2. These extensions have a meaning and are standardized. For example, -7 is a handheld, and -1 till -4 is a good choice for our LoRa trackers. The following parameter is the path. Default is wide1-1, which means that if a Digipeater receives your packet, it transmits it. If it hits a second Digipeater, it is no more transmitted. This makes sure the network is not flooded with messages. So, wide1-1 is okay for the current LoRa APRS networks. The second number, by the way, is always 1. Two other parameters can be changed, the symbol and the overlay. They determine how your tracker is presented on APRS.fi. Here you see the available symbols. Standard is the / and the bracket, which leads to a runner symbol. The Space Shuttle would have used / and S, for example. The other parameters should be left if you want a tracker compatible with the existing networks. If you want to build your own network, you can change the frequency or the spreading factor. You can also reduce the output power, which is set to the maximum, 100 mW or 20 dBm. Only in the rare case you use an old version of the T-Beam, you have to change the environment to version 0.7. Next, you have to upload the code to your T-Beam using a USB cable. Just hit this arrow and choose the correct COM port. Do not forget to upload the configuration file by selecting it and hitting this command. Now your tracker is ready and displays your call sign. You should also see it on APRS.fi if you have a LoRa iGate in your vicinity. If not, you have to proceed to the next step. Create your own iGate or Digipeater. Also here we can use a prefabricated board. Because this board does not need a battery nor a GPS, we have a wider choice. I use this LoRa 32 board. You have to follow the same steps as with the tracker, just with a different software. You can leave the board on default and again adapt the configuration. This time there is more work to do. The file is called is.cfg.json and is also located in the data directory. Again, we have to add our call sign. This time a -10 extension is proposed. If we want to build an iGate, we have to connect it to the internet and choose a static IP address or enable DHCP. I use DHCP and leave the rest on the default settings. Next are the Wi-Fi credentials and the message, which will be displayed on APRS.fi. If you want to place your iGate on the map, you have to enter its position by copying the coordinates from Google Maps. Using a T-beam, we could enable the GPS module, by the way. For iGates, you must fill out the passcode field. It can be obtained from this homepage. Just enter your call sign without number extension. This number is not a secret, but it is needed for iGates which transfer messages to the APRS network. I leave the APRS server as is. Other regions select the respective server. And now it is an excellent time to look at the APRS network itself. Because it has to transfer thousands of messages every hour, it uses load balancing and a hierarchical structure. If you use one of these rotate addresses, you will automatically be connected to an available server. Because the network does not store the messages, other services like APRS.fi, APRSdirect.de or APRSmap.info store and display them in a browser. You also get apps for your smartphones to access APRS.fi. It is also possible to transfer messages across APRS, but this is not supported by this project. Next is the Digipeater and the beacon section. If you have no internet available for your device, you can configure it as a Digipeater that transmits the messages over the air. This is an unmanned station and you have to check if your license allows to operate it. I never used the FTP or the syslog function, but I enabled MQTT and filled in the MQTT broker's address and credentials. Now I get all messages received by my iGate as an MQTT message, and I could use it to trigger an action. I put my iGate into one of these wastewater pipes and added a 3D printed holder and a ground plane antenna. Because I have other receivers on my roof, I connected it to the 5V supply of a close-by device. Otherwise, you would have to add a power supply. The connection to the internet is made by Wi-Fi, by the way. You get also a small PCB if you want to connect it directly to Ethernet. Attila DL1NUX compared standard with LoRa APRS. He found out that LoRa was more reliable despite 10 times less power and a smaller antenna. And a last story. Andreas, OE3DMB, used this technology to track the position of his car via the QO100 geostationary satellite, with this short antenna and a 20-watt amplifier. The QO100 is 36,000 kilometers away, by the way. We deployed 10 iGates around where I live, and German hams did the same at the other side of the Rhine River. So we are pretty much covered here. When do you start your project in your area? That is all for today. As always, you find the relevant links in the description. 73 to everybody, and please consider supporting the channel by using the links in the description. See you in the next episode.